Well, welcome everybody to Steel for Lunch. As I have been saying at the beginning of each one, this is a relatively new program. We're trying to spread the word. So anybody who is enjoying these sessions, please tell your friends about it. It's on Friday at noon, almost every Friday, and the schedule is available at steelcenter.ca. So it's my pleasure today to introduce from S-Frame Software, Matt Sauer, who will be giving us a presentation on staged construction analysis and steel design in S-Steel, which is a component of S-Frame. And he'll give us some insight into what these special features of S-Steel can do. So with that, thanks for joining us, Matt, again. And I'm going to turn it over to you.
Absolutely. Well, thank you guys for your time. I'm just going to share my screen. Let me know when you can see. I'm relatively new to this program, so. Can you guys see my screen yet?
Not yet.
Okay, I think I got it here.
Yep.
Okay. Perfect. So sorry about the delay getting that started there, but again, welcome today. My objective is to educate you a little bit more about stage construction analysis in S-Frame and, as Professor Driver mentioned, S-Steel as well. And for those of you that have never used S-Frame before, you may not have heard the term stage construction, or at least not in the context of S-Frame. You may have seen it in other applications. So basically, stage construction analysis will almost introduce another domain to your analysis where you can consider the time effects of when you're building the structure, how it's responding. So looking at analysis and design process, not just at the very end of the design, but also how it's being erected, how the structure is responding during that time, and what needs to be done to ensure that it's stable and safe. And this is available in S-Frame Enterprise, which at the Steel Center you guys all have access to. And basically it allows you to work on your structure in increments that might represent a more realistic building scenario. And I apologize, some of these graphics are maybe somewhat concrete focused, not for any particular reason. My colleague helped me develop these slides, and so some of them were done kind of with his influence of concrete backgrounds. So you can imagine that when you start building a structure, it's not going to look exactly like the finished product does right away in most scenarios. So you have to work on it incrementally. And it's going to be exposed to various loading conditions during that time, whether it be construction loads, wind, its own self-weight, and so on. And also the structure may not necessarily have all the stability systems built into it to resist those normal loads. And you have to make sure that it doesn't collapse during that time. So if we're looking at various conditions of this completeness of our structure, it's important that the engineer considers those in the overall design. So here's just a few examples that we might see where we have essentially 4 very different looking structures, but they all work up to be the final design. And we have to be able to analyze them at each stage and make sure that they're safe, robust, and able to resist the loads that are required. So this allows us to evaluate the structure behavior during and after the construction process, whereas normally we'd only look at it after the structure has been erected. It also gives us another capability that I'm going to touch on today that allows you to compare 2 similar but potentially different structures. And actually, you could do more than 2. I'm just using 2 in my demo. But basically, it allows you to look at different alternatives of the same structure within one interface, one S-Frame model even. So it's very easy to compare models that way. And this is integrated with our steel design and also our concrete design software. So you can easily and quickly co-check and design your steel structure, or if you have concrete, even concrete as well, within this interface and the stage construction approach. And we'll go through more details as we go through the demos today. So we're going to talk a little bit more about stage construction analysis. We'll also look at how the steel design is built into this. Since our topic focus is really more on steel with this group, I'm not going to go into the concrete design aspect because it follows a very similar workflow. And frankly, I think if you know how to do it with steel, which is, I'm imagining what you guys will be more interested in, the concrete process will be very similar. We'll then look at some multi-scenario analysis and design and go through a Nest Steel example of that as well. At the end, I'll just make a few summarizing points. And of course, just as we always have done, if there are any questions at the end, you're more than welcome to ask. You can also interrupt me at any time during this presentation if anything comes up. So as you can see here from this presentation, we're really focusing on two methods for utilizing the stage construction approach. One where we actually look at the various construction sequencing or construction stages, and the other where we compare two different approaches to designing the same structure. But let's start with a bit more background on stage construction. So why would we want to do this? Again, I've already maybe elaborated a little bit on this, but I'll go a little bit further. This enables you as a structural engineer to get an accurate assessment of your design as it goes through the design or construction process. So you can perform a structural analysis at any one of the stages that you define, and it's up to you to define what those stages are. You can go into as much or as little detail or increment, I guess, discretization as you'd like to in this process. And it also allows you to perform the code checking of the steel and concrete components according to whatever design codes govern your design at these various stages as well. So you can look at the behavior before, during, and after construction and set up preload conditions. So you can imagine that if you were to assemble a frame and start with the lower story first, that's going to be exposed to different types of loads prior to the addition of the second and third and fourth stories. So there may be some settlement, some loading that's already occurring before you even add on those second stories. That's what we consider preload. And as the user, again, you can define what the preload conditions are on different stages as you go through this process. So we'll look at an example here where we have a 3-story structure. And at stage number 1, I'm just going to look at the ground floor. So we have our columns in the ground floor and the beams above our columns. And you can see here we have 3 bays in the X direction, 2 bays in the Y direction. We're then going to add a second story onto that in stage 2. But as you can imagine, during stage 1, we're exposing this, this part of the model to various loadings. Obviously, self-weight is going to be one of them, but we can consider other loads, like maybe there's some construction load or some materials on top that are going to cause settlement. They're going to cause some sort of deflections, you name it. Any sort of reactions to those loads can occur in stage 1. And so by the time we add stage 2 on, we may already be dealing with some deflections within these columns. Some axial forces might be induced in these columns and moments in the beams and so on, and then we're adding stage 2 on top. So that would be an example of what we can consider a preload. And we might have more preload by the time we add stage 3 on top, and that might be not only in stage number 1, but also stage number 2 or floor number 2. And we don't have to stop at 3 stories. We can keep going as long as we want, but this example that I'm going to go on is just a 3-story structure. So I'm actually going to jump into SRAM right now and walk you through the process. And I've cheated a little bit because I actually have the model constructed for me. I think by now most of you are probably familiar with how to build simple frames in SRAM. If you're not, we have a lot of resources and you're more than welcome to reach out for me for help. But I'm really not going to focus on kind of the initial modeling process that we do in this webinar. What I am going to focus in on, though, is just maybe illustrating a little bit more about what this model represents. So obviously, we now know that there's 3 stories, and It's all constructed here, just like you would construct any other model. I have my section properties defined, and in this example that one of my colleagues in the UK office of SRAM actually built for me, he's using British sections, so that's why some of the nomenclature might look a little strange for those of you that aren't familiar. We have steel beams, and we have concrete columns. And I'm really going to just focus on the design of the beams, but again, we can also analyze and even design the concrete columns if we want. And if I just right-click here, we can see here that this is all the section properties are being inherited from the database that I've grabbed it from, the European database. And I've defined this 450 by 450 millimeter concrete column, and all the section properties are calculated for that as well. Now looking at the support conditions, we can see that we have a fully fixed base on all of these columns. Nothing too exciting there. We've also separated the model into different folder groups here, so I can look at maybe a set of columns just on the ground floor, on the top floor, or the middle floor, depending on what I'm interested in. Now let's switch our attention over to the loads, because I do have a few different loading scenarios that I want to look at. So I have 3 load cases in total. I have a self-weight load case. And for those of you that have never defined load cases in SRAM, how a self-weight load case is defined is you click on the new load case button, and then you would just define this gravitational factor in the Z direction of -1. And that's going to just calculate for us the mass of all the elements in our model based off the length of, in this case, we just have members. So the length of those members multiplied by the cross-sectional area of those members, and then multiplying that, which would be the volume of all our members, by the density of our materials. So we already have material properties assigned, so it's able to calculate those self-weights for us based off that information, and it's going to apply it using the gravitational constant for the unit system that we have. We're using metric units, so it's 9.81 newtons per kilogram, and it's going to apply that in the negative Z direction with a factor of 1. So 1 times 9.81. Now we have some other load cases. I have a dead load, and I can actually just look at my member loads here and joint loads and see what that represents. So for my dead load case, I have 75 kilonewtons per meter on the top floor and 100 kilonewtons per meter on the bottom and the second floor. And for my live loads, I have something similar, just larger magnitudes, but basically all the beams are being loaded in these 2 load cases. So I'm really only looking at gravity loads right now. And I do have a load combination defined, just a single one for illustrations purposes. So if I go to the edit menu under load combinations, I can see what this represents. So it's basically just using a factor of 1.0 for all of my load cases. So 1 times self-weight plus 1 times dead load plus 1 times live load. And if we just scroll over to the right-hand side here, we can see exactly how that's defined. We just select our load case and then enter the combination factor for each. Now you may be wondering, well, so far this is pretty much how I would normally work with SRAM anyways. Where does the stage construction process actually start? So to do that, you would first go to the settings menu. And under the settings menu, you go to preferences, and you just have to turn on stage construction. So if I go to the solver tab of the preferences window here, we have this option. It says sequential construction options available only in Enterprise Edition, which at the Steel Center and at University of Alberta, you guys have access to. I'm just going to toggle on this option here that says this structure will be modeled and analyzed using a stage construction sequence. Make sure that's turned on. I'll press OK. And the only thing that on the surface really happens here that you'll notice any differently, if I would just move this aerial window out of the way, is that normally we would see the list of all of our folders that we've created here, and there would be no tabs at the bottom. But now we can see that we have a tab for model organizer and then another tab for construction stages. And if I click on the construction stages tab, you can see that I actually have 3 different stages defined now. And these are created in exactly the same way we would define a folder in SRAM. If you've already done that, this is done in a very similar way. You just right click here and you say new stage. Now I have 3 stages already defined. And so again, I set up this model ahead of time just to save me a little bit of time during the demo. And if I look at this here, I can see that stage number 1 just has the lower floor. Stage 2 has the lower floor plus the floor above it. And stage 3 has everything. Now I can actually right click on one of these existing stages, and I'll start with stage number 1. And I can right click and I can go to find more information about it. So I can look at things like the construction, stage status, and preloads. And here I get a little dialog that shows me the information related to my stage status and preloads for every stage in my model. And it gives us a little bit of a description of what's happening here. So it says update stage preload description with this description. Stage 1 will be analyzed for load cases and combinations. Load case 1 will be used as a preload. Load case 1 being our self-weight. And you can see here that I can tell SRAM solver whether or not I want to analyze for just the load cases, just the load combinations, or the load cases and combinations for this particular stage. So we actually do have quite a bit of control over this. And in this example here, we have stage preload description. So stage 1 will be analyzed for preloads only. However, it says load case 0 will be used as a preload for stage 1. Now we don't have a load case 0. And that's kind of expected because stage 1 is our starting point. We don't have anything before stage 1 really. So we don't have any prior deflections or axial loads or anything that we can keep in this stage from the previous stage. So that's why we see this here. Now for stage 2, I can look at this and I can see, okay, well, I have something similar here, but I'm actually going to make some updates. I'm going to say that I have my self-weight load case that's going to be used as my preload. So I'm just going to use this option here, stage 2, set this self-weight to preload. You notice I say stage preload is going to be a load case, and I'm going to select this one and just click update. And I'm going to do the same thing for stage number 3. Stage 3, self-weight, preload, and update. So I just made sure I did this for all my stages. And now I can go ahead and actually analyze my model. So I can click this Analyze button, which looks like a set of footprints. Or I can go to the Run menu and then Analysis. And we're running a stage construction analysis, so I'm going to run a linear static analysis. And again, here I have another option to exclude preload for all stages, which we'll see an example where we might want to click this later on. And I'm just going to click OK. I'm going to click OK to run. And we can see here what's happening when we go through the analysis. So basically, the analysis is broken up into 3 phases. We have stage 1, where we're analyzing. We're going through the analysis of all 3 load cases and our load combination. And just pay attention to the dynamic and memory allocation. Normally, you wouldn't really need to pay attention to this, but it might highlight kind of how this is approaching the analysis. It's 25 kilobytes there. Then we go to stage 2, it goes through the exact same process, but now we have 51 kilobytes. And in stage 3, we have 73 kilobytes. So basically what's changing between these is the amount of members that are being examined by the analysis solver. We have more dynamic memory allocated when we have more members, more elements, because it's a bigger model in that scenario. So the solver is ignoring anything above stage 1 for this first phase, and anything above stage 2 for the second phase. That's why we have different amounts of memory allocation. Again, you wouldn't really need to look at that closely, but hopefully that helps with the illustration of what this is doing. And now I can start looking at some of my results. So right away here, I'm looking at my stage construction sequence here. And if I go to stage number 1, I just want to make sure it's selected and it will have this plus sign next to it. I can look at some of the results. So here, maybe I want to look at reactions. I'm just going to toggle off the display of the unselected elements so it doesn't overwhelm you with all these different lines and so on. And you can see that we're getting some reactions within our model, but I'm really interested in the FZ reactions. I'm getting about 233 kilonewtons for the self-weight. If I go to stage 2, you can see that that number is pretty much doubled, which makes sense because we have basically the same thing just added on top. So 465 kilonewtons. And in stage 3, where we have even more loads. So again, in this scenario, this preload is our self-weight loading. And we can look at the analysis results. Maybe we want to look at deflections here. So we can see that we do get some deflections. We get very small deflections at the top of our columns. But if I go to properties, we can actually drill down into it a little bit more. So this may be hard to really notice. Perhaps maybe I should have used a larger load to illustrate this better. But we're getting about 0.01 millimeters if we round up this the translation. When I go to stage 2, we're getting a little bit more deflection because obviously not only do we have the preload from the original load case, but we're adding another load in the sense that the self-weight of all the other loads on top is also being applied. And in stage 3, well, we don't get that much deflection over on this side because most of the load is on the other side, but we can see that we're getting some more deflection here where we have the other floor being added on top. And maybe it's better illustrated on this right-hand side. Now I can look at other loading scenarios, not just the self-weight. If I want to look at my load combinations, for example, I can see those here as well. And I can see the deflections related to the load combination that I might experience at any one of these stages. I'm going to go back into the slides and just describe a little bit more about the stage construction process, specifically how it relates to steel design. So as I already mentioned, this model contains a mix of steel and concrete, and we're really just going to focus on the steel right now. You can see here that we have some I-beam sections assigned to our beams, and for our concrete columns, it's just a square concrete column. Rendered it here in S-View as well, just so you can get a better idea. So now I'm just going to jump into S-Frame again, and we're going to run this through S-Steel. So just go to the stage construction sequence here, and I'm just going to click Build Steel Design Model, or I could go to Run S-Steel. It will do the exact same thing. And you notice that when we're in S-Steel, even if I have stage 3 selected, it's only going to show us the steel material members, the ones that S-Steel recognizes. It doesn't care about anything that's not steel, essentially. So it's ignoring these concrete sections. And if I double click on them, I get a message here saying member cannot be code-checked. It's section not found in steel database or section not supported by S-Steel. It's not surprising since it's a 450 millimeters square concrete column. S-Steel is not going to be the right tool for that. We could use ICD, but again, that's not really something we're going to concern ourselves right now. So what I'm going to do is I'm going to work through each of these stages, starting with stage 1, and I'm going to code check them. So code checking, for those of you that aren't familiar, is just basically comparing the demands versus the capacities on our model. So we'll start with the stage number 1, and I'm just going to use a load combination. And I'm going to code check, click OK. So we get some utilization ratios. Again, these are the demand versus capacity ratios for these elements. Then I'm going to go to stage number 2 and do the same thing and code check. You can see we're getting something similar there. And then go back to the code input, stage number 3, and I'll code check this for the load combination as well. And you can see the utilization ratios. Now let's really drill down into this a little bit closer. Maybe we can select a few beams to pay close attention to. So I'm going to look at these beams on the bottom floor, maybe 1.366 and 0.697, because those will occur in all of our stages. So remember, for stage 3, it's 1.366, and for stage 0.697 for this beam in parallel with the x-axis. Now, if we go to stage 2, we're getting something similar for this longer beam, but 0.701 for this beam right here. Whereas before it was actually a little bit less utilization on it. And for stage 1, now this beam has jumped up in terms of its utilization, 1.711, and 0.806 for this beam. So it's actually increasing the amount of utilization that we get as we go down in the stages. So let's just try to get a better understanding for why this is happening. If I right click on this beam and I go to code details, I can get an idea here looking at some of the utilization ratios. So the governing code check that I had in this scenario was strong axis bending and axial force stability interaction. This is the clause that it's related to. And I'm actually going to be using, for this example, I'm using the European code. Again, this was an example my colleague gave me. So I'm recycling that, but the paradigms that we use will be very similar. So we can see here that it's basically related to strong axis bending and axial force. And this beam is in bending and compression. We can see the axial load here, 97.3 kilonewtons of compression. Now, if I work my way up to the next stage and look at this beam again, I'm going to right click, go to code details, and just scroll down until I find the governing check, 0.701, strong axis bending and axial force strength interaction again. But these ones are also very close to my governing utilization check as well. And if I notice here at the top, now this beam is in bending also, but it's in tension this time. So now we have an axial load of 71.9 kilonewtons of tension, different than what we had before, where it was in compression. So that's already starting to make a little bit of sense. And if I go up to stage 3, where we've added this top floor, and I right click on this beam, then we can go into code details again, and I can see that it's still in tension, and we're getting an axial load of 77.6. I think that's actually a little bit less axial load than, a little bit less tension than what we had in the previous example, if I'm not mistaken here, but we're getting, again, something very similar. All the utilizations seem to be governed by the strong axis bending and axial force strength interaction. But obviously it makes a difference depending on whether it's in compression or tension. And we can see that by looking at the individual stages all at once. In different scenarios, it's going to experience different types of loading, and the interaction between axial force and bending can play a large role in what that utilization is. Now, this is kind of a hand-picked example. It may not always behave this way, but the nice part about having this stage construction sequence is that you're able to go in and look at these details very clearly. Now, we could also do the same thing with our concrete columns using the integrated concrete design, which you guys also have access to if you're curious, just under the build concrete design model or run. It would be from SRAM actually. If I go back to SRAM, run, and an S concrete ICD. But we won't get into that right now. Let's move a little further ahead and talk about stage construction analysis and how it can be used in a comparison between different scenarios for your analysis and design. And first of all, let's explain why you would actually want to do this. Well, first of all, we have a lot of engineers that will come to us comparing multiple alternatives to come up with the best possible solution. And sometimes it can be tricky to balance multiple models and update those models and maintain them and maintain as much consistency as possible between them while still comparing the results. So this allows you to build the single model and then differentiate it through the stage construction approach, where you might assign different sections to different members during a certain stage, or you might deactivate certain elements during a certain stage. And you can compare the structural analysis results very easily between these stages. So rather than considering in this scenario, we have the stages name may not necessarily be quite the best term to use. You could also consider it as maybe an alternative rather than a stage. And of course, you can still tap into the power of SDL and the ICD to compare the code check results. So I'm going to compare two different examples here. I have design scenario 1 on the left-hand side and design scenario 2 on the right-hand side. And if we look at the left side a little bit closer, you can see here that we're using different roof beams, first of all. So they're tube section roof beams. And also, if you're looking closely, we don't have any bracing on the left-hand side. And the base of our columns is also pinned. So we do have some differences between these two scenarios. Where on the right side, obviously we have these braces, just in this bay here. We have our roof beams represented by wide flange sections, and the columns are fixed at their base. And we're going to compare these two using the stage construction approach, but rather than having these as different stages, they're going to be two design scenarios. So let me just open up the model that I have ready for us. And I don't need this file, so sorry, I don't need to locate that. So as you can see here, this model on the surface, again, looks just like any other model that we would have in SRAM. We've built this up. We've assigned certain sections. We've actually got some extra sections because we're changing the sections between different alternatives. We want to make sure that they're all there for us. We've also got different types of, I don't think we got any different materials here, but we got different support conditions that we're going to be considering as well. Now, just as before, we want to set this up for a stage construction approach. So I'm just going to go to the settings menu, preferences, and just show you again where that's done under the solver tab. We just want to make sure that this option is checked. And again, normally this would be used for sequencing or staging your construction process, but in this scenario, we're actually using it to compare different scenarios for our model. So we have our construction stages tab here. And we have two different scenarios represented. We have design scenario number 1. And you notice when I left click on design scenario number 1, it grays out all of these brace members because they don't exist in that design scenario. And for design scenario number 2, they appear again. So I'm just going to focus in on design scenario number 1 again, just explain a little bit more in terms of what we're doing. So you can see the sections that are being assigned. We're using section number 2 for our columns, which I think is consistent through all the other elements, or the other alternative as well. But I have section number 5, which is a tube section. I can render it if I'd like. And I can see that tube section represented here. Maybe I'll just hide the unselected objects so I don't confuse myself with those hidden braces there. So we can see we have a tube section for roof beams, and we're using a wide flange section just on the top of these columns. We also have pin supports on our model. And if I turn off the display of our rendering here, I just want to check to see if we're using any releases. Doesn't appear to be the case. We don't have any trusses or anything, so this is a moment frame that we're dealing with. Now comparing to design scenario number 2, here we have some trusses that have been added. These are brace elements, but they're axial elements, meaning that they don't support any shear or moment. They're just basically accepting tension and compression. And these have been added only in design scenario number 2. We can see here the loading scenario, or the section properties that we've assigned. So we're using that wide flange section again for our roof beams. And again, I just want to confirm to see if we're using any moment releases. Doesn't appear to be the case, so we don't use any releases in this example, but we do have some trusses in this bay. So I would imagine that this would probably be the more expensive scenario to build, given that we do have some trusses and we have fixed base columns. Maybe they're not the most realistic scenario to compare, but who knows, maybe you guys have an application where you'd want to consider these two options side by side. Now I'm going to look at the loads window and look at the types of loading that we have. So we have roof load, self-weight, obviously. Our roof loads are being applied to these beams aligned with the y-axis. I have snow loads, again, applied to those beams as well. Wind loads in the lateral direction on the columns. And the crane loads are actually member loads being applied to the ends of these cantilever elements. I also have some load combinations. So two of them here. I have load combination 1, which is considering load case 1 and load case 2. And you can see load combination 2 as well. And I'll just drill down into these. So a few different loading scenarios being considered. Let's go ahead now and run the analysis. So I'll run a linear static analysis. Again, we're comparing these two stages as two different phases in the solver. And you can see the dynamic memory allocation is slightly different, but more or less the same. We're not having as big of a change between the stages as we did in the previous example. This is just asking me for a view file, this VU7 file, so I'm not going to worry about that. It's one that my colleague sent me this model. I forgot to download that model or that part of it, but it's only required if you wanted specific views of the structure. So let's look at the stages a little bit closer. And actually, I should have shown this earlier, but if I right click on the stage when I go to the loads window and I go to stage construction sequencing here, I haven't actually assigned any preload to these different design scenarios, which is my intention. I don't want to have them preloaded. I'm actually considering two different scenarios side by side, not a sequence of events. So sorry, I should have mentioned that earlier. And if I just repeat the analysis process again, I also wanted to indicate here that under stage construction options, we're deliberately excluding the preload from all stages, just in case we had applied them earlier on in the stages. I had made sure that was turned on because I'm not intending for these to be, back-to-back stages in the construction cycle. So here I can look at the results. I'm just going to look for the results at load combination number 1. Obviously, we can look at things like the reactions. So for this load combination number 1, which considers self-weight and my dead loads, I have a reaction for design scenario number 1 of 581.56 kilonewtons. Design scenario number 2, 629 kilonewtons. So obviously, design scenario 2 weighs more. It's got the bracing and everything, which makes sense. I can also look at things like displacements to see how the model is faring due to these applied loads. And this isn't a real structure, so some of the magnitudes might be a little bit high for our liking, but we're just taking this with a grain of salt. 37 millimeters of displacement in the vertical direction along the roof line here. I've exaggerated deflection view just for the sake of illustration. So that's design scenario number 2 with the bracing. Design scenario 1 actually has higher displacement, which probably isn't a huge surprise because we have the pin supports. We also have no bracing. So we're getting a little bit more displacement of this. But you can see how quickly and easily it is to compare these two. If I want to look at the moments in my model, in this case here, I can see I'm getting a maximum moment along this beam for design scenario number 1 of, what would it be, 181 kilonewton meters for design scenario 1, whereas design scenario 2, I'm actually getting slightly more than that. So maybe not the best example because they're pretty close to one another, but you can kind of get an idea. I can also look at the bracing forces, and I can see what sort of bracing or axial load I'm getting in my elements and how that compares between these different stages. And with this, we're going to jump into S-Steel as well and compare the different results. So I can look at the results between these two examples and see how they might, again, fare according to the comparison between demand and capacity. So I'm going to just jump into S-Steel here, clicking on the Build Steel Design Model. And starting with design scenario number 1, I'll hide all the unselected objects. We can see what we're using in our design. And I'm just going to go to Run, Code Check, and code check just this according to load combination number 1. And here we can see that we're getting our utilization ratios. It seems like our beam capacity is being exceeded only in these lower beams here. 1.654 for our utilization ratio. Now let's jump back to the code input window and go to design scenario number 2, where we are considering the inclusion of these braces as well as the different type of section that we have for our roof beams. And I'm going to code check this one according to load combination 1 as well. Click OK. And you can see we're getting the same utilization for these roof beams, but now we're getting some utilization issues here with our braces as well. So this would help us weigh the options. Is it worth us adding these braces, changing the roof beams to I-beams and so on, or should we just consider using those tube sections? If it may be more economical, it may be a better approach since we do have the same failing members down here. We would need to upsize those anyways. And we can right click on them and see, okay, well, let's look at the code details for these sections. And they're actually unloaded. There's no loads or no significant loads going into them. We're ignoring loads below a certain threshold. But it's still going through the slenderness check, and it's found that that's actually an issue due to slenderness. But all other things considered, we're getting pretty low utilizations when we have these tube sections in our roof beams. But when we use design scenario 2, where we have the braces and so on, you can see that we're getting higher utilizations in these roof beams, and we're actually getting failing utilizations in these braces as well. And this is again due to the slenderness ratio. So maybe not something we have that much control over. With the types of elements, we can always increase the section size and so on to combat that. But we would have to then make the decision, okay, is it worth us having these braces and having pin supports and I-beam sections on our roof? Or should we consider design scenario number 1, where we have lower utilizations, but we are also using different type of section here. And we have fixed base supports. We're also getting more deflection from the load combination out of this example as well. So it helps us compare these two alternatives. I'm not trying to say one is better than the other. I would say that if you have a scenario where you're not sure what's best, you could utilize this approach and then easily compare the two scenarios side by side and make a more educated decision that way. And you saw from the reporting, we have the ability to generate these reports out of S-Steel and the same thing out of the integrated concrete design. So you can generate those and you don't have to document it yourself. It will produce these reports for you automatically for each stage. And you get the clause references according to the different design codes that you're considering. So this is an example again of the steel design code check, where we can see which members are failing, why they're failing, what might need to be done, and we can have S-Steel optimize as well if we wanted to. So today we talked about stage construction analysis. We introduced a little bit of the background behind it, why it might be useful, when you might want to use it. We looked at an example where we went through basically a sequence of construction stages, starting with the ground floor, then the top or the second floor and the third floor, and comparing the results between those. We then looked at a different use of stage construction in SRAM, where we considered multiple analysis options for a specific structure and compared them side by side, looking at the analysis results and then the steel design results. I just have a few summarizing points, and then if there are any questions, I'm happy to answer them at the end of the presentation. So with the stage construction analysis, we're able to look at the assessment of different construction sequences that our structure might go through. We can also compare two similar but different models within a single SRAM file. And within either one of these options, we have the full steel and concrete design suite built into that as well. So not only are we looking at analysis results, but also design results and the potential for optimization. And of course, you get the detailed report generation from SSteel and the ICD, but you can also generate reports from SRAM as well to look at deflections, shear forces, moments for your model and how it's set up in each one of these stages. So before I open up the floor for questions, I also just want to let everyone know about a few upcoming events from SRAM. We actually do have more than this, but I wanted to kind of focus in on the things that haven't been changing so far. We're kind of revamping some of our schedules, so we have a few changes in the air right now. One of them that's for sure going ahead as scheduled is next week's nonlinear and P-delta analysis online training course. I think that's one I talked a little bit about when I was doing the P-delta presentation last week. So that's September 28th to October 2nd. It's a 3-day course, but it's quite a lot of material that we're covering. So I think it's 10 hours of instruction over that time, Monday, Wednesday, and Friday. It starts at 10 a.m. Pacific Standard Time or Daylight Time, so that would be 11 a.m. your time. We also have a couple more webinars coming up in October and November and training courses as well. Because our training course schedule and our webinar schedule has been going through a little bit of flux lately, just to make sure that we have something coming up for October, I would say take a look at our website, www.s-frame.com, under the support link to find the latest up-to-date schedule. When I made this, it was before all the changes had taken effect. So some things were still up in the air. And thank you for your time. Again, you can reach our website at www.s-frame.com. And keep in mind, we do more than just analysis and steel design. So if you have any interest in other topics, feel free to reach out. And thank you for your time. If there are any questions, I'm happy to answer them now. If not, thank you and have a great weekend.
Lovely. Thank you so much, Matt. We'll just give it a couple of minutes to see if anyone has any questions. Please feel free to send them over on the chat. You can see that at the bottom of your screen, or just unmute yourself and go ahead.
And while we're waiting as well, I just wanted to thank everyone for their time today. I know you have a number of different topics that you've heard from me, as well as plenty of other vendors. I think this is a great option for engineers looking to expand their technical skills and their knowledge. So thank you for organizing this.
Okay, so I think that's it for questions. Well, thank you very much, everyone. And thank you, Matt. Again, we had Matt from SFrame presenting today. It's really exciting and always great to see the quirks and features, I guess, of SFrame and their software suite. I want to give a huge thank you to all of our industry members, to the Steel Center. They're on the screen. And I'd love to encourage you, everyone, to check out our upcoming presentations as well. Our next week's one is on QNect, which is a revolutionary connection design software. So stay tuned for that, and please go ahead and invite your friends or colleagues. This is open to everyone, not only strictly within the U of A. Awesome, lovely.
Well, thank you guys, and have a great weekend.
Yeah, thanks, Matt. Cheers. Have a good weekend, everyone.